And we're going, okay, so last time we were talking about Green's theorem, right? And sadly we got up to the point where we were able to write down Green's theorem, and then the time ran out and we didn't have time to do anything with it. So let me just remind you where this comes from. We were talking about this thing called circulation, right? We talked about circulation. I mean, line integrals measure the extent to which a fluid is flowing along a curve. Well, if the curve is closed and so therefore it kind of goes around in a circle in some sense, then if the extent to which the fluid does that, same thing, reasonably could be called circulation. Okay, so we defined this quantity, and then the next thing we did is we observed that it has this weird eyebrow-raising feature called accumulation, right? So you can take a region, a two-dimensional region, look at its boundary circulation. You can chop that region in half or in however many pieces you want and look at the boundary circulations on all of those individual pieces, and amazingly, they add up. The whole is the sum of the parts, right? So that's surprising, and it's remarkable when something has that feature, right? Said differently, it means it kind of behaves like stuff. It's like it's a physical kind of stuff. And physical kind of stuff, of course, distributes over the interior. You can talk about how much of it is. Right? If you have mass, that's a physical stuff, you can talk about its density. How much of that mass is distributed throughout the interior. Well, so likewise then, because of that accumulation feature, we can do an analogous thing for circulation. We can talk about circulation density. And this quantity here that I like to write as green F, right? Otherwise known as Green's operator or Rote F or curl. And I hope nobody's going to use this one. I really don't. I don't care for that one, so let's not use that one. But anyway, it is in the book, so you can if you want. But this density, circulation density, computed by that formula. Right? So altogether then, what we have is, I'll leave this boxed. What we have is a theorem that says if you're interested in computing circulation, you can do so with a double integral over the interior region bounded by that curve. Really, really surprising results. These two integrals are computed over different domains. Right? This is the boundary curve. That's the interior region. Very weird. Okay, and now we can actually do an example. Let's go to the next page here. This will be our first example, and we're going to, let me get this. There we go. We are going to look at this curve, the clockwise oriented unit circle. We're going to look at this vector field, given right there. Oops. And then we're going to compute the circulation. Right, okay, let me not jump the gun. We're going to compute the vector line integral of that vector field over this curve. So, first observation to make is that this is indeed a closed curve. Right, and so being as it's a closed curve, I can call it circulation. All right. Okay, now, we do need to figure out how to view this curve as being a boundary. Right, now I want to come up here, back up here to the theorem, and emphasize this theorem, Green's theorem. You can compute that line integral with this double integral. Has a big catch to it. There are some regularity issues concerning the vector field. It's got to be continuously differentiable. Okay, let's not get bogged down in that. That's not really the point I'm trying to get at here. The big sort of like what's the word here? The big catch is that this curve has to be a boundary. There it is. It says so right there. This theorem does not say any line integral you feel like can be computed with a double integral. What it says is that if you have a line integral over a boundary, right? Clearly indicated. So if we're going to use this theorem, we have to make sure that our curve actually is a boundary. Now, before I go on to doing that for our example at hand, let me show you what kind of trouble you can get into if you kind of forget this little point. If you have a line integral over just some curve, that's not a boundary. Right? Not a boundary of any sort of a region at all. and you say, well, I want to compute a line integral f dot dx. And if you just kind of forget about that fact that it's not a boundary of anything, and you just say, oh, it's a line integral, and Green's theorem allows me to recompute line integrals as a double integral of Green's operator, and let's see here. Oh, what if it were to turn out that this were equal to 0, let's say, and by the way, that does happen. In fact, it happens, I'm going to say often. You're computing a line integral. You sloppily invoke Green's theorem. You compute Green's operator and get 0, and then you understandably say, oh, I've got a double integral of 0. This integral is 0. Right? Very tempting to write that down. And it's complete nonsense. It's complete nonsense because this curve here, right, that curve was supposed to be a boundary. And it isn't, right? Remember, it's not a boundary. If it's not a boundary, I'll point out the really awkward question, or an immediate awkward question that comes up is, notice the domain for the double integral has to be the region whose boundary is your curve. Right? If your curve is not the boundary of anything, then there is no double integral over which to even talk about doing a double. There is no two-dimensional region over which to even talk about doing a double integral. So there is no Green's theorem. It's not that Green's theorem doesn't apply; it's that there is no theorem to apply at all. Right? And you see, I subtly swept that point under the rug over here by just leaving a great big gap there as to what the domain for this double integral was. The whole point is that there is no domain to even talk about. Right? So everything that I've got written down on the bottom half of the screen right now, this is all garbage. Right? There is no application of Green's theorem for a curve that's not a boundary. Does everybody see what I'm talking about? Really dangerous landmine. Something got to make extra sure to be careful about. Okay, that noted. Back to our example at hand. Is this curve, the clockwise oriented unit circle, is that curve a boundary? Close, but not quite. Right? You got to keep in mind the word boundary. This symbol here, right, means boundary, and boundary means oriented, and furthermore oriented in a prescribed particular set way. And this curve, this C that we're given, is going the wrong way. Right? It's going such that the region is on my right. That's not the rule. I need to be going around where it's on my left. So our curve is not a boundary. The easy resolution in this case, though, is to point out that if I were to just go the opposite direction around the same curve, right, talk about C minus, right, same curve, opposite orientation, that is a boundary. And specifically, it's the boundary of, well, exactly what you think it is. It's the boundary of that region D that I've got highlighted in yellow. There. All right, so how are we doing? Is everybody with me so far? Okay. All right, so before we invoke Green's theorem, then I do have to worry about the setup here. I'm going to recognize first that for orientation reasons, right, I need to view this in relation to the curve going the opposite way, and going the opposite way, I accordingly get a minus sign on the value of the line integral. First observation. Second observation to make is, as noted here, that curve is indeed a boundary. C minus is a boundary of a two-dimensional region. And with that set up, now I can finally invoke Green's theorem in regards to this integral right here. Right? That integral, it's an integral over a boundary. Integral over a boundary is a double integral of Green's operator. And of course, now don't forget the minus sign, right? This minus sign, well, here, let me do it like this. This minus sign here comes along for the ride, of course. Is everybody with? Yeah, question.
Can we do this Green-oriented curve thing?
Say it one more time.
Can we do this for like every oriented curve that encloses a region to the right? Like,
So whenever your orientation is going the wrong way, an analog of this trick here, just recognize that you're going the wrong way. So you're going to look at the curve with the opposite orientation. Got to be honest. You got to put that minus sign in to make up for it. Once you've got it oriented the correct direction, it's a boundary, and you're in business. Absolutely. How we doing? Everybody okay? All right. Okay. All right, and at which point it's all over with the shouting, right? I mean, Green's operator, how do we compute Green's operator? Well, the rule for Green's operator, let's see, I've got to take dq dx. Okay, so I take the second component, take the x partial, that gives me 3. And from that I subtract, I've got to take the first component, partial with respect to y, which is 1. So Green's operator turns out to be really convenient here. It's just 2. And then I'm doing a double integral of this constant, this convenient constant, over a garden variety geometric shape, namely a disk, unit disk. And so the calculation's easy. What do you think? Everybody happy with how that ended up? All right. Okay, now just for comparison purposes, let's entertain what would our alternative for this have been if I had computed this directly. It's tempting to look at the integrand and say, that integrand doesn't look that bad, but keep in mind you're doing this around a circle, and when you parameterize a circle, x and y become cosine and sine. That means that even though e to the x, you see e to the x, it doesn't seem that bad. That's actually e to the power of cosine t. That's weird. Right? And likewise, there's going to be various different kinds of weird and undesirable that are going to show up there if you were to actually parameterize and plug and chug. So this would be a very inconvenient, at best, plug and chug, but it's a snap with Green's theorem. Okay. All right. So here's a twist on that same sort of situation. Here my curve is going to be made up of line segments, specifically that start at the origin and then successfully and in order go through these vertices, thus making this kind of what I'm going to call a sort of a triangular figure 8 curve like that. All right, there's our curve. The question is to compute the line integral again. And so, let's see here. I've got to ask myself if I want to use Green's theorem, which I do. Not that I could. Look, I could brute force this. Look, the vector field's not that bad. The curves are straight lines. This is doable, right? But it's a bunch of numbers. It's going to be inconvenient. If I want to use Green's theorem, I got to start from the same place and ask myself, wait a minute, is this a boundary? And if so, how, or is it made up of boundaries? Plural, and if so, in what way? Okay, first observation to make. This first line segment is equivalent to that line segment paired with that line segment. So I can break the pieces in half and nothing happens. Next, this trio right here is a boundary. Right? It's the boundary of this region D1. So those three parts, that half, if you will, the left half in some sense of the integral that I want to compute is, it's straight up, it's a boundary of that triangle. Everybody with me? All right, now awkward point. The remainder that I have here, that, not a boundary. Now it encloses this region D2, but it's not the boundary of D2 because it's not oriented the correct way. And so, all right, so is this a boundary? No, sadly it's not. But this is, however, the opposite orientation of this trio of curves, which is a boundary. That's the boundary of this. Again, I'm going to try to fill this in there. It's the boundary of that green region. Right, so we've got this green region D2 over here. Its boundary is this dark blue curve. And we want the exact opposite of that boundary to finish up our actual curve we're interested in. So how are we doing? Is everybody with me? Okay. All right. Okay, so with that noted, then again we can just kind of slowly and carefully write this down. The curve that I'm interested in, I can think of that as being boundary of D1 plus, and then sort of the opposite orientation on the boundary of D2. So this first line is just recognizing what we've already observed. Next step, we recognize that this minus sign, this change in orientation there, gives you a minus sign on the value of the integral. So you might say it's as if we kind of factor out that minus sign. And now we're in business, because now we have that right there is exactly a boundary line integral. So I can use Green's theorem. And this over here is exactly a boundary line integral, and so there I can use Green's theorem. Is everybody happy? Okay. A little bit of algebra shows what Green's operator is. Again, this computes from the original field. Here's our original vector field, and x partial of the second component minus y partial of the first component, and you compute that out, you get 9. And now you've got a couple of easy double integrals, and easy because the domains are constant, and also easy because those domains are, the integrands are constant, and these domains are have easy to compute areas, and even better than that, those two areas are clearly equal, right? And so we're subtracting two equal values, and integral is 0. All right. What do you think? Everybody okay with that? Okay. So yeah, Green's theorem is really nice. You do have to be really careful with orientations. You also have to be careful to make sure that you only apply it when your curve is actually a boundary. Gosh, that's a huge one. It's really sad when this happens. But if you write down something like this on an exam, if it should turn out that curve indeed is not a boundary, then everything to the right of the equal sign is nonsense. This doesn't mean anything. So very, very dangerous little landmine. Make sure not to step on that. Always check and make sure that your curve is a boundary. Okay, moving along. Here's a nice application of Green's theorem. I'm going to start off with Green's theorem. Here it is. That's the Green's theorem. Sorry, I forgot to click my thing off here. There's Green's theorem. Specifically, this is Green's theorem applied to that special vector field right there, 0, x. You'll see why it's special in just a moment. But let's take a moment to recognize all this is Green's theorem. Boundary line integral, double integral of Green's operator. All right. So, first thing I'm going to do with this is observe that right there is just x dy, and so this is just notation. This is not a big deal, nothing to worry about. But this left side of the equation of Green's theorem, I can rewrite as integral x dy. And this result that I'm working my way up to is typically, historically, more often written as integral x dy on the left-hand side. It's just notation. This is a rare circumstance in which I actually like the coordinate notation, because check it out, it's a little bit more compact, right? The vector notation a little clunkier. Usually not the case, right? But in this case, it's a little bit more compact and convenient. So, how about that? Okay, on the right-hand side, we can compute this Green's operator. It's just 1. Right? X partial of the second component is 1. Minus the y partial of the first component, clearly 0. So 1. And that's by the way, that's what's nice about this vector field. That's why we're interested in this vector field, this special vector field 0, x. Green's operator is exactly 1, which then allows us to compute this integral easily. Integral of 1 just gives you area of your domain. And so all together then, the punchline is that this line integral computes the area that the curve bounds, which is unexpected and kind of interesting. Okay, everybody with me? Okay. You may be thinking to yourself, you know what? All else being equal, I think I'd rather just compute an area. Right? So I don't want to compute the line integral, so I'm not going to use this result. Hold your judgment. Just a second here. To be fair, there is work to be done to compute a line integral. But if you have a straight line segment, right? Straight line segment that starts at one point, goes to another point, straight line in between. For straight line segments, these integrals are really easy to compute. Look how easy it is. The simple formula for integral x dy, if you're talking about a straight line segment, average value of x, change in y. It's easy as that. That's really convenient. So if your curve, now obviously a straight line segment cannot be a boundary. Right? But several straight line segments together absolutely can be a boundary. And in those cases, being able to compute each segment individually with this simple little formula, very, very handy. Let's see this in action. So let's look at the polygon that we have here. This nightmare of a polygon right there. Yeah. What's the area? Okay, well, yikes, I think is a reasonable response to that. I mean, you'd have to break this up. If you were going to take a regular high school geometry approach to this, you'd break it up as that triangle plus, see if I can, there's a little annoying little sliver of a triangle there, and then there's that triangle, and then there's, oh gosh, that triangle, I guess. Oh, and then there's that triangle. You can see why I don't like this. And then there's that triangle, and then there's that triangle. What a nightmare. How many is that? 8? 7? It's too many, whatever it is. So, plus, none of these are right triangles. Okay, that's a nasty approach. Really hard for computing that area. So let's not, right? Let's take the other approach here. We're going to look at the curve one segment at a time. Let's look at this first segment here, and let's ask, what is the average value of x? Well, x starts at 1 and ends at 12, and that averages to 13.5. Right? The sort of the average. There. 13 halves. Sorry. Let's see. What is the change in y? Well, y starts at 1 and ends at 6. So y changed by 5. Right? So average value of x times change in y. And then I can compute the way that contributes to my area. Right? Area is the sum of these line integrals, any one of which is just x bar delta y, and so that contributes 65 halves, apparently, to the area. And then just keep going. Right? You go all the way around. Do the same calculation for that edge. There's x bar, there's delta y. Contributes that much, and et cetera, et cetera. Now, just to be thorough, let me do the fourth one here. Oh, whoops! Come on, fourth one there. Right. So, fourth edge. Let's see. The average value of x is 3. Right, and then the change in y. And here's the little subtlety. Y started at 8, ended at 4. Y decreased by 4. So note minus 4 here. right? Change in y is also oriented, right? We were going specifically down here. Down means y changed for the negative, so -4. Is everybody on board with that? Okay. All right. So you just keep going all the way around. I know there's a bunch of edges. What is it? There's 9 edges total here, but if you compute all 9, that gives you all 9 pieces of the line integral. You add those up, add up these numbers, and 19. And notice I didn't have to do any obscure, weird geometry. I mean, Heron's formula, I think, was likely to come up. That involves square roots. The side lengths themselves would be square roots. That'd be really, really weird and ugly calculation that would mysteriously end up at 19 and we wouldn't have any sense for why, right? But much easier to just do this. No nasty arithmetic. The worst thing about this arithmetic is I guess that there's a 2-digit number there. Okay. Oh, there's a fraction. Oh my gosh, there's a fraction. That's, denominator of 2. Right? Not that bad. Yes?
How come adding them all up will give you the area of the inside?
Yeah, so what we've got is that the entire line integral is what actually tells us the area, right? But when you compute an integral, you can break up that integral into pieces. So rather than compute, all at once, let's see here, rather than all at once try to do this whole thing. There's too many pieces, right? What I'm going to do is compute that one first, and then that one second, and then that one third. And I claim that altogether, blue plus orange plus purple plus all of these others, altogether that is the green perimeter line integral, and that's what equals the area. Yeah, is that satisfying? Mm-hmm. Okay. All right, everybody else happy? All right. Okay, so let's see here. Moving along. Another application I want to talk about. I'm going to have to develop a new idea, slightly new idea. We're going to talk about something called flux through a curve. Y'all remember, of course, we've already talked about flux back in chapter 3. And flux, well, it was 3-dimensional. We talked about how much fluid is flowing through a surface. Well, if you have a 3-dimensional fluid, you can talk about how much flows through a surface. Likewise, though, if you have a 2-dimensional fluid, you can talk about how much of that 2-dimensional fluid is flowing through a curve. So flux through a curve, that same idea, right? You can do a calculation analogous to what we did in chapter 3 if you're curious. But I argue that the longer the curve is, the more fluid's going to be flowing through it. Right? Kind of stands to reason. And then also the extent to which the vector field is pointing perpendicular. Right? The normal component of the fluid flow. Right? Don't really care about the parallel component. Going parallel to the curve doesn't go through the curve. But the normal component, the perpendicular component, tells you how fast fluid is flowing through each little piece of length, and altogether, this product be reasonable to suspect is going to tell you something about how much fluid is flowing through that curve. Now that's the hand wavy, quick and dirty version. If you want to see the fully detailed argument, you can just go back to chapter 3, see where that 3-dimensional argument is, and just copy that, reduce the dimension by 1, everything would be analogous. Okay. All right. So that's the idea of this thing called flux through a curve. Okay, so we're going to now talk about a related thing, boundary flux. Boundary flux, it's just flux. Flux through a curve, but that you're computing across the boundary of a region. So a boundary is a curve, and so you could reasonably talk about how much flux there is through that boundary. There is another convention here. Anytime you see the word boundary, you should have a knee-jerk reaction, an instinctive sort of fear little chill goes down your spine. Or boundary, oh gosh, orientations. What's the deal with orientations? Anytime you see the word boundary, orientation matters. So when we're talking about boundary flux, the convention is outward. This also is an arbitrary convention, right? You remember with talking about boundary orientations along a curve, we arbitrarily said go such that the region's on your left. Arbitrary but standard. Likewise, this is arbitrary but standard. Okay. Alrighty. So, here's a region. Again, focusing on just part of the region. Here is the boundary curve there. And how am I going to compute the total boundary flux? Well, I'm going to break this curve up into little pieces, such as this little piece there of size ds. Right? Let's talk about how much boundary. Let's apply the boundary flux formula to this little piece ds. And our flux is that right there. Right? So F dot n times the length of the piece of curve, and the length is ds. All right? And then if I want to know the total over the entire curve, right, then I just do an integral. Namely, I add up all the pieces over the entire curve, over that entire boundary. And so what I get then is my formula for flux is this thing right here, integral f dot n ds. Let me pause before I go on. Does everybody see how I got integral f dot n ds? Questions? All right, here's the bad news. We have not previously talked about how to do integral of a vector field dot in ds. We've seen dot tds. We have not seen dot in ds. All right, so how do we deal with that? Here's the cool trick. F and N. There they are. There's F, there's N. Keep in mind N going outward. Let me just point out that if you were to rotate counterclockwise by 90 degrees, right? Take these two vectors, F and N, just rotate counterclockwise 90 degrees. Well, they would turn into T and what I'm calling F perp here. So specifically, normal, right, perpendicular to the surface when you rotate gives you tangent along the surface. And furthermore, outward will rotate into in the direction such that the region's on your left. Right? So N literally rotates into T. Our good old familiar unit tangent vector. Okay, that's nice. P comma Q rotates to negative Q comma P. That's just a Math 218 90 degree rotation. Again, make sure you remember how rotations are linear transformations, which are matrices. Columns are the images of standard basis vectors. All that linear algebra jazz. And applied to P comma Q, you get negative Q comma P. Make sure you can do that. Make sure you're comfortable with that. Come to office hours if you're not comfortable with that part. So who cares? Why would I care that I can rotate these two vectors and get these two vectors? The thing is that when I rotate the pair of vectors, the lengths don't change. The angle between them doesn't change. And that means that the dot product doesn't change. And that means that F dot n, this F dot n that I'm interested in here is equal to F perp dot T, which I like better. Because I like this T. I know how to deal with that T. Right? Okay, so that's the quick little move there, and we are all set up now to do the calculation. TDS, we're back into familiar territory. This is a regular old vector line integral. TDS is dx. So I've got here a boundary line integral. I have here literally a circulation. Now it's a circulation of this other vector field called F perp. But still, this is a circulation line integral, and we have a powerful theorem about circulation line integrals called Green's theorem. This circulation of F perp is a double integral of Green's operator of f perp. Okay. Is everybody okay with that? I'm just going to punch it up now. Green's operator of f perp. Let's see here. Now, make sure to recall when you're doing Green's operator, right? It's tempting to memorize the letters dq dx minus dp dy. You really can't do that here. It's the x partial of the second component, which we normally would call q, right? But in particular, x partial of the second component, that being p, and then minus the y partial of the first component, in this case being minus q. Everybody see that? Yeah. Okay, so there's Green's operator, and these minus signs here cancel, and so we're left with just dp dx plus dq dy, which you may recognize from Chapter 3. We've previously discussed that expression. That is divergence, this thing called divergence. And so altogether then, we did this kind of a tedious little calculation. The punchline, though, is that flux is computed. And let me circle this differently. Flux, aka a kind of a weird line integral of sorts, is computed with this double integral of divergence. And for whatever it's worth, this is our first glimpse of the divergence theorem. This is the two-dimensional version of the divergence theorem. There's a three-dimensional version that we're going to talk about later in Chapter 7. Divergence theorem. Boundary flux computed as an interior integral of divergence. Everybody happy? Okay. Alrighty. Okay, let's see an example. Suppose you want to compute the flux of this vector field through outward through the unit circle as our curve. Okay. So now again, you could brute force this, and again, let's not, because it'd be a nightmare. Circles means trig. Trig in these places would get weird, right? Okay. Flux outward through the unit circle. Outward-oriented unit circle is a boundary, right? It's the boundary of the unit disk. So I can just invoke the divergence theorem. I was asked for a flux. Flux is a integral of divergence over the interior. The divergence now is not a hard calculation. I got to take the x partial of that plus the y partial of that. This gives me -3. And now I have a super easy integral over constant over a garden variety geometric shape, namely the unit disk, and we're done. We saved ourselves loads of trig and u substitutions and probably integration by parts and such. How do you feel about all that? Everybody good? All right. Okay. Moving along. So, previously, up here, how did I get this theorem? How did I get the two-dimensional divergence theorem? Well, I got this basically by invoking Green's theorem, right? Green's theorem was the powerful trick here. I had to kind of play around to relate flux to the original circulation, and once I invoked Green's theorem, I had to kind of play around to rewrite, Green's operator of f perp. I had to, recalculate that to realize that it's divergence. But basically, the heavy lifting here was done by Green's theorem. That's where the magic happened. We turn a line integral into a double integral. Oh my gosh, that's the big step. And everything else is kind of details. So, in fact, this is regularly referred to as a variation of Green's theorem. Right? And that's fine if you want to think of this as a variation of Green's theorem. Neat fact, though, you don't have to use Green's theorem at all. You can throw out Green's theorem and just make the observation that boundary flux is also an accumulating quantity. not hard to argue that it is. If I look at this left piece and ask, well, what is the boundary flux of that left piece? Well, the boundary flux of the left piece is like this. It's outward oriented boundary flux, like so. Right, there's the boundary flux of the left side. Then there's also, what's the boundary flux, outward oriented boundary flux of this right piece? Okay, well, there's this, again, oriented outward. Right? So, outward oriented boundary flux of the left plus outward oriented boundary flux of the right. Does that equal to the outward oriented boundary flux of the whole? And it's tempting to say no. There's a difference. The difference between blue plus orange and purple is the difference is these two pieces right here. Right? These aren't part of the outward oriented boundary flux of the whole. I've gotten too much stuff in here left over, and at a glance it looks like it's not going to work out. But you got to keep in mind, these two pieces of outward oriented boundary flux are on the same curve with opposite orientations, and they cancel. So there is no difference then between the whole and the sum of the parts. Everybody buy it? It's kind of morally equivalent, I like to say, morally equivalent to what happened when we were talking about circulation. Shared edge, part of the boundary of two pieces, but with opposite orientation, so they cancel. That's exactly what happened when we were looking at Green's theorem. Shared edge, part of the boundary of two different pieces, but with opposite orientations. Now, this way, opposite orientations, two different directions along the curve. Whereas here, yeah, sure, a little different, opposite orientations through the curve. So, yeah, different appropriate to the context, but strategically, right, morally, same idea. So, that said, once you realize that you've got an accumulating quantity, right, boundary flux is an accumulating quantity, then we can treat it like any other calculation that we do in terms of densities, right? Mass, because it's an accumulating quantity, mass is not just defined on a whole. Mass is defined locally. You can see how much mass is in each little piece because it's an accumulating quantity, and those little pieces of mass relate to areas by way of a density that we call mass density. Right? And then likewise, we've already seen Green's operator, same story. Little pieces of circulation relate to area by way of circulation density. And in exactly the same way, divergence relates little pieces of flux to the corresponding area as they are that is the flux density. So this is a really common term, by the way, very common use in physics classes, and I'm going to go ahead and suspect that in engineering classes, you'd think physics, engineering, probably culturally similar. When I was taking physics classes as an undergrad, I heard the term flux density more often than I heard the term divergence. And I really like this term because it gets at the point. I mean, the reason that divergence does what it does is because it's a density. It's because this is what you multiply by size to get this accumulating stuff called flux. Thus, flux density. How are we doing? Is everybody with me? Everybody happy? All right. Okay. So next thing, I want to talk about the fundamental theorem of calculus again. I know that y'all know the fundamental theorem of calculus. I want to take a weird point of view on it, but I think in a way that's really helpful to digesting all of this business here. Students naturally get a little creeped out by the idea that, wait a minute, what do you mean flux density? Flux is computed on the boundary. What do you mean it's coming from the interior? kind of hard to get comfortable with that idea. I want to point out you've seen such a thing before with the fundamental theorem of calculus. We can view the fundamental theorem of calculus as being about a quantity called change. Looking at 2 points, x1 and x2, you can talk about how much the function changes between that starting point and that ending point. And it's not hard to persuade yourself that that is an accumulating quantity. If you look at how much the function changes from here to here, and then how much the function changes from there to there, the sum of those individual changes gives you the total change. Right? Make sense? Okay. So, you might not have thought of it this way, but you can think of change as accumulating. You can think of change as being distributed throughout the interior. And the convenient thing is you can actually kind of see that happening. So here's a picture of the function. I might want to keep track of its change, right? Looking at this graph right here. If I were to ask how much does the function change over that interval, well, you would look at the value of the function there, and you'd look at the value of the function there, right? And so you would measure the change by computing f of b and f of a and subtracting. Said differently, you compute change on the boundary. But, is that where the change happened? Now, come on. You can see the change in action, right? The function's not changing along in here at all. And you can literally see the change happening. Like that, right? So the function is changing. The actual change is happening there. Right? You measure change on the boundary. But the reality is, unquestionably, change happens in the interior. Everybody see what I mean? So I claim it's the same for these other theorems that we've been talking about. This one's just easier to visualize. Because I can look and see, oh yeah, look at that, check it out, it's actually changing. Right? It's harder to look at a picture of a vector field, and see flux, boundary flux is a little weirder. Circulation, kind of hard to visually. It's just a visual problem, right? But it's structurally the same as this. All right. So, furthermore, the integrand here, f prime, I claim is our change density, right? That's telling you how much of the accumulating quantity of change is happening for each little piece of size of the domain, right? So f prime is change per unit size. It's quantity, accumulating quantity per unit size, and quantity per unit size is how we think of density. So again, this is a density. So f prime, when it's large, is telling you, there's a lot of change happening there. Per unit size, of course. And when it's small, it's telling you, there's not much change happening there. And again, this is also old news, right? You can see that f prime is large along in there, indicative of the fact that there's a lot of change happening at these points in the domain. Well, of course it is. It's right there in the picture. Of course you can see it. Look at all the change happening, right? F prime, it's just so, I don't even know how to say it. It's an old interpretation of the derivative. F prime's telling you how fast the function's changing. Right? So, again, twisting the interpretation just a little bit here, it's telling you how much of the accumulating quantity of change exists in this part of the domain. The bigger the density, the more of the accumulating quantity. Okay. All right. So just as an example, and this is a silly example, I apologize for wasting it. Just to set up the analogy, though, if you look at this function here, f of x equals x squared, there's a total change of 9. Right? Grand total, the function changes by 9 over the given interval from 0 to 3. So is more of that change happening at the point 1 or at the point 2? Right? Where is there more change happening? picture. Well, that's steeper over here at 2. Of course, there's more change happening at 2. But from a density point of view, at 2, we can compute the change density. Change density is this formula right here. It's the derivative, right? That gives us a formula. And you can see that as indicated by the graph, the change density is higher. 4 as opposed to 2 here, right? So algebraically, the derivative, change density, is doing what we can, in this case, we're fortunate enough to be able to see it in the picture, as obviously, of course, there's more change happening there. Okay, so in the same way, Green's operator is a way of telling you how much, I'm out of time. Okay, I'm gonna quit here, but foreshadowing for Monday, we're going to find that Green's operator does the same thing. It's just telling you how much of the circulation that you detect on the boundary, how much the circulation is happening and where. Okay, all right. See y'all later. Real quick about the exam, in case you're curious, I'm almost done with the grading. My hope was to get the grading finished this afternoon. It didn't happen. A bunch of nonsense came up that I couldn't get away from. So this weekend, at some point, I should have the exam graded. Next real quick point. Feedback seems clear that the true-false questions were hard. And I really got you. Yeah. So 2 things. First of all, I want to reassure everybody. Yeah, sure, there were hard questions. There are supposed to be hard questions on the test. It'll all wash out in the curve, right? I'm not gonna, on the 4-point scale, there will be no difference, right? So the curve will be correspondingly generous, you might say, to account for that. So it's not going to be a problem. The other thing I want to say is that I did talk to several students about the true-false and possible ways of doing it in future exams, and the consensus seems to be that there's just a pretty serious lack of enthusiasm for it, which wasn't my I thought true-false was going to be liked, but I guess anyway, it doesn't matter. It wasn't. So I have no plans of going further with true-false questions in this class. So it'll just be regular essay-style questions from here on out. Okay, see y'all later. Have a great weekend. Yep.